Hello everybody, we're going to solve this problem together, and here it is. The original observation deck of the Empire State Building is on the 86th floor of the building, which is 1,050 feet above the ground. A penny is dropped starting from rest, and it falls straight down until it hits the ground. Starting from rest is important, make a note of that. And we're going to please neglect air resistance and the wind for this problem just to simplify things. So this is more of a theoretical problem. So let's begin with part A. Determine the position function of the penny. Here is the formula for position function. This was in our notes today. Okay, it is 1/2 gt squared plus v naught t plus s naught. G is the constant acceleration due to gravity, and since we are on Earth, G is not going to change too much. So we need to plug in G equals -32. V naught is the initial velocity. Since we started from rest, our velocity at the beginning is 0. 0 feet per second. So if you think about it, when you're holding a penny in your hand and you drop it, at that moment when you drop the penny, it's not moving at all, it's moving at 0 feet per second. That's its speed, or velocity is our stronger vocab word from today. And then S naught is the initial height above the ground. And we are standing this far above the ground. Okay, so to determine the position function, we need to plug in those three values for G, V naught, and S naught. So -32 for G, 0 for V naught, and 1,050 for S naught. And let's simplify things. 1/2 of 32 is -16. That's -32, sorry. So it's -16 t squared plus 0 times t is still 0. And then 1,050. 0 plus 1,050, that is still 1,050. All right. Moving on to B. B, we are to determine the velocity function. And a reminder from class, this is just equal to the derivative of position function. So what we do is we write our velocity function, v of t, takes in time t as an input, and this is equal to limit as h goes to 0 of s of t plus h minus s of t all over h. And another way to think about it again with notation, this is s prime of t, the derivative of the position function. I already wrote that. Okay, so what we need to do is, first of all, let's figure out off to the side here what values we need. We know that s of t, which is given to us, we found it in part A, is -16 t squared plus 1,050. Next, we need to calculate s of t plus h. And we're going to plug in both of these values into the formula so that we can find the velocity function. S of t plus h is -16 something squared plus 1050. Now, I'm going to erase t right here, and I'm going to replace it with what I'm plugging in. And I'm plugging in t plus h. So it is t plus h quantity squared. Now those parentheses are important because when you square t plus h, you're multiplying t plus h multiplied by itself. So this is the expression we end up with, -16 times t plus h plus 1050. And I'm going to do a quick FOIL and skip the details and tell you that this is t squared plus 2th plus h squared plus 1050. Distributing the -16t, and I think I'll be done with this part at least. -16t squared minus 2 times -16, so that's -32th, and then minus 16h squared. And I'm still adding on that 1050 at the end. Okay, I think we're ready to go. We're ready to plug this in. Remember, you need to keep writing limit. So limit as h goes to 0 of step 1, plug in s of t plus h. So that is -16t squared minus 32th minus 16h squared plus 1050. And then I need to subtract s of t, which is -16t squared plus 1050. And let me move this stuff. Alright, that stuff was a little bit too close to the problem there, so moved it down a little bit. Alright, so this is our fraction. We plugged in s of t plus h, that's the red stuff. Subtract s of t, that's the green stuff, and it's still all over h. So the next thing we're going to do is distribute the negative sign, and you still need to write limit. Limit as h goes to 0. All the red stuff is just going to stay the same. Minus -16t squared, so that's plus 16t squared, and then minus positive 1050, so that I'm subtracting 1050. And it's still all over h. Then I take the limit as h goes to 0 of, some stuff should cancel, so I see that I have 1050 and a -1050, those are gone. And then -16t squared and positive 16t squared, those are also gone. Those cancel. Those add to 0, so I don't need to think about them anymore. So here's what I have left in the numerator, all over h in the denominator. Alright, we're nearing the end. Most of the hard stuff is gone. We just need to do one more thing here. We need to factor an h out of the numerator. So take an h out on top, and -32th, all that's left is -32t, minus 16. If I take an h from h squared, then I still have one h remaining. So that is -16h all over h. And I have an h on the top, h on the bottom. Those are going to cancel out. So I have limit as h goes to 0 of -32t minus 16h all over 1. Now, I don't really need to write all over 1 because anything divided by 1 is itself. So I'm just going to write it like that. And then here is where I finally take the limit, so I can stop writing limit. So I'm going to use direct substitution, and I'm going to plug in 0 for h. -32t minus 16 times 0. And 16 times 0 is just 0, so we have -32t. And this is our velocity function for part B. Alright, and do remember that velocity is going to be in feet per second, just as a side note. So when we calculate velocity later, that's going to be the unit. Okay, so next we need to determine the average velocity of the penny on the following intervals. From 4 to 7, from 4 to 6, and from 4 to 5. So when it says from 4 to 7, that means from t equals 4 to t equals 7. For the next one, that's t equals 4 to t equals 6, and so on. So these are t values, or time values, that they're given. So from 4 seconds to 6 seconds, 4 seconds to 5 seconds, so on. So let's do part 1 first. So we do need our position function. I'm going to rewrite it here just to have it handy. And let me make sure I got this right. Negative 16t squared plus 1050. Yes. Alright. So at 4 seconds, where is the penny? How far is it above the ground? If I plug in 4 for t, that's what the position function tells me. So I'm going to plug in 4 for t in this equation, and that'll tell me how high the penny is above the ground. 4 squared is 16. And negative 16 times positive 16 is negative 256 plus 1050. Alright, so let me just do the math out here. 1050 minus 256. Let's see, we need to carry this, so that's going to be 9, 14, 10, 4, 9, and 7. 794. Okay, so at t equals 4 seconds, penny has height 794 feet above the ground, of course. If we're thinking of this as a point on the graph, the coordinates would be 4, 794. Okay, so here's what we do next. Let's get the coordinates for 7. Or t equals 7, sorry. So when t equals 7, I'm going to plug in 7, and 7 seconds have passed, so it should be pretty close to the ground by now. Whoops, I'm going to plug in 7 for t to this equation. Alright, so that's negative 16 times 49 plus 1050. That's negative 784 plus 1050. And then what we want to do here is, of course, subtract. Just a quick subtraction here. 10 minus 4 is 6, 6, and 2, 266. So we are now 266 feet above the ground. So what this means is after 7 seconds, the penny has height 266 feet. And then again, if we're thinking about this graphically, as a coordinate point on the graph, it would be 7, 266. Okay. Alright, so now that we've done the work, our formula for average velocity is equal to the change in distance divided by the change in time. Kind of like speed, right? If you go 60 miles in 1 hour, that means your actual speed is 60 miles an hour. So you do how far the penny traveled on the top, and you can find that by subtracting the distances, so 794 minus 266, and we're going to have that divided by 4 minus 7. How much time elapsed? Okay, so 794 minus 266. That's 528. And on the bottom, 4 minus 7 is negative 3. Now when we divide these together, let's see what we get. negative 176 feet per second. So what that negative sign means is penny is moving down, which of course we knew because we dropped the penny and gravity is pulling the penny down towards the earth. But that negative sign just tells us that, hey, this is a velocity. So if it's negative, the penny's moving down. And if it's a positive number for our velocity, that means the penny is going to be moving up, which won't happen in this scenario. Another way to think about this, if that was kind of confusing, is this is just slope. And you know how to find slope. Slope is y2 minus y1 over x2 minus x1. That's the slope formula, right? So I'm going to label one of these points x1, y1, and I'm going to label the other point as x2, y2. Now, just to be consistent with the way I already solved it, I'm going to call the point on the bottom x1, y1, and I'm going to call the point on the top x2, y2. But you could reverse x1 and x2, and it wouldn't matter, as long as you're consistent with y1 and y2. So you'd get 794 minus 266 over 4 minus 7, and clearly that's the same as above, so you'd get the same answer. Alright, let's move on to number 2. Alright, so for part 2, we need to find the average velocity on 4, 6. So really, we're going to do the same thing as in part 1. And this time it's half the work, because we found s of 4 in part 1. That's 794. So now in part 2, I just need to find s of 6, and then I'll apply that average velocity formula. So this is our position function, negative 16t squared plus 1050. So we plug in the 6. Let's replace t with 6. And this is negative 16 times 36 plus 1050. That's negative 576 plus 1050. And then if I subtract these two together, let's see what I get. 0, 9, 14, and 10. So that's 4, 7, and 4. 474 feet above the ground. So at 6 seconds, we're at 474 feet above the ground. Now, if you want a more detailed explanation, look at part 1. I went over why we do this. This one, I'm just going to kind of skip what these numbers mean and jump straight to the formula. So change in s minus change in y. It's 794 minus 474 over, let's see, I went this way, 794 minus 474, so I need to go this way with my t values, 4 minus 6. Alright, I'm going to bust out the calculator now. That is 320 divided by 2, and that's a negative 2 because 4 minus 6 is negative, and that is negative 160. This is a velocity, so that's negative 160 feet per second. The number is negative because the penny is moving down. That's why there's a negative sign. Alright, on to part 3, and that is the average velocity on 4, 5. So again, we already found s of 4 in part 1. Now we need to find the position of the penny after 5 seconds. So we plug in 5 to the position function. So I'm going to replace t in the position function with 5. And then we have negative 16 times 25. 5 squared is 25. And this is negative 400, yep, plus 1050. And I add those together, and that is, I think I can do that one in my head, that's negative, positive 650. Alright, so now we get our average velocity. Again, if you want to see a more detailed explanation, what the numbers mean, the better understanding, watch part 1. I'm just going to jump straight to the formula here. Velocity is change in s over change in t, so that is 794 minus 650. That'll give us the distance traveled. And I subtracted the numbers this way, so I need to subtract the t values in the same way. So that's 4 minus 5 on the bottom. So 794 minus 650 is 144 divided by negative 1. So I get negative 144 feet per second. Okay, so we found the velocity on these ever shrinking intervals, 4 to 7, 4 to 6, 4 to 5. Now we're going to determine the velocity at t equals 4 seconds. So what we do is we plug t equals 4 in to velocity function. We found the velocity function in part B. It was negative 32t. And let's just double check. That's correct. View t equals negative 32t. Yep. So this one is actually pretty straightforward once you know what to do. Plug in 4. And negative 32 times 4 is negative 128. And reminder, the units we're working with are feet per second. So after 4 seconds, the penny's been traveling for 4 seconds. This is how many feet it moves in 1 second at t equals 4. So that's moving pretty fast. And let's check out part E now. Okay, so E asks us to find the time required for the coin to hit the ground. Too many commas. Alright, so when a coin hits the ground, its height, or position, is 0. So here's what we need to do. Here's our position function from part A. And remember that t equals time in seconds, and s equals position, which really is height above ground in feet. So the strategy here is you set s of t equals to 0 and then solve for t. Right? Because when its position is 0, that means it's 0 feet above the ground. That means it's hitting the ground. So, pretty simple. Once you know what to do, this is good review of Chapter 2 stuff, polynomials. You change one side of the equation, s of t side to 0, and then you solve for t. Now this is a quadratic, right? It's t squared, but there's no middle term. So the fastest way to solve this is subtract over 1050, and then divide both sides by negative 16 to isolate t squared. I'm going to need a calculator for this. So that's 65.625, and then if you want t, take the square root of both sides. So t is, let's see here. Let's say t is approximately 8.10 seconds. Now, so that's not that long. 8 seconds after you drop a penny off the top of the Empire State Building, it will hit the ground. And it accelerates faster and faster and faster. So the question is, how fast is it going when it hits the ground? And that's part F. Find the velocity of the coin at impact. Now from the previous part of the problem, the coin has impact on the ground at t is approximately 8.10 seconds. So here's what we do. If you want to find the velocity at any given time, you just plug the time into the velocity function. So plug t equals 8.10 into that handy dandy velocity function. Alright, so we do v of 8.10, and that's equal to negative 32 times 8.10. And let's bust out the calculator. And remember, our units we solved in part B, our units were feet per second. So that is the velocity of the penny when it hits the ground. Alright, now just for fun, from Wikipedia, something called muzzle velocity, that is the speed of a bullet with respect to the muzzle of a gun at the moment it leaves the end of a gun's barrel, i.e. the muzzle. So the end of a gun's barrel is called the muzzle. Now, firearm muzzle velocities range from approximately 390 feet per second to 1,200 feet per second in black powder muskets, and to more than 3,900 feet per second in modern rifles. So what do you think about the question above? Could this penny actually kill someone? And the answer is, according to this problem, maybe. Look at how fast this penny is going when it hits the ground. Remember, negative means it's moving downward. So it's almost moving as fast as a gun. So it seems like it might kill someone, but it turns out air resistance and wind actually play a huge factor. So the penny would get blown away from the building, and there'd be a ton of air resistance pushing back up. So this video has a great answer to this question. If you want to watch this video, the link is on the assignment. Or if you don't want to watch the video, you can just kind of read this article. It's pretty short. It explains why the penny probably wouldn't actually kill someone. It would just give them a really bad headache. So that, again, I'm advocating you throwing pennies off of buildings. Don't do that. You could definitely hurt someone. But I hope this answers the question. So I will see you next time. Thanks, everybody.